electrical load calculations, specifically for residential applications, determining the demand rating for appliances like electric ranges is crucial. The National Electrical Code, or NEC, provides guidelines for this. An alternate math method exists for simplifying the calculation of an electric range's demand rating. The primary method involves multiplying the range's wattage by a load factor to account for realistic usage patterns. The alternate math method streamlines this process. Here's how it works. Firstly, you multiply the range's wattage by a factor of 0.6. For instance, if you have a 16,000 watts range, you would multiply 16,000 watts by 0.6. Secondly, this calculation provides the demand rating. In the example of a 16,000 watts range, multiplying by 0.6 results in a demand rating of 9,600 watts. The explanation for this method lies in the NEC requirements for calculating the demand rating of electric ranges. The formula specified by the NEC is demand rating equals range wattage multiplied by load factor, where the load factor equals 0.6. This load factor serves as a multiplier that acknowledges that ranges are not consistently operated at their maximum capacity for prolonged durations. By applying a load factor of 0.6, we effectively reduce the demand rating by 40%. This reduction provides a more accurate and realistic estimation of the actual electrical demand imposed by the range. The alternate math method simplifies the application of the load factor by directly multiplying the range wattage by 0.6. The outcome of this simplified method is identical to that obtained using the formula specified in the NEC. It is important to understand the reasoning behind the use of a load factor in these calculations. Electric ranges, like many appliances, have a maximum power rating. This rating represents the power the range would consume if all its heating elements were operating at their highest settings simultaneously. However, in typical use, a range rarely operates in this manner. For instance, only 1 or 2 burners might be in use at a time, or the oven might be set to a moderate temperature. The load factor accounts for this difference between the maximum possible load and the typical operating load. The NEC provides specific guidelines and tables for determining the demand factors for various types of loads, including electric ranges. These guidelines are based on statistical data and real-world observations of appliance usage patterns. By using these demand factors, electrical designers and installers can ensure that the electrical system is adequately sized to handle the expected load without being unnecessarily oversized, saving on material costs. While the alternate math method provides a quick and easy way to calculate the demand rating for an electric range, it's important to remember that it is a simplification of a more comprehensive calculation. In more complex situations, the NEC provides more detailed guidance on how to determine the demand factors for different types of loads. For example, NEC Table 220.55 provides demand factors for household cooking appliances over 1 and 3/4 kilowatts rating. This table is used to determine the maximum demand for ranges, wall-mounted ovens, counter-mounted cooking units, and other household cooking appliances. The notes to Table 220.55 provide additional guidance on applying the demand factors. For example, Note 1 allows you to use the demand factors in column C for ranges of not over 12 kilowatts rating. Note 2 provides a method for increasing the maximum demand in column C for ranges with a rating greater than 12 kilowatts. Specifically, the maximum demand in column C must be increased by 5% for each kilowatt or major fraction thereof that the range rating exceeds 12 kilowatts. Note 3 allows you to calculate the nameplate rating of a range consisting of a separate oven and cooking top by adding the nameplate ratings of the oven and cooking top. These more detailed calculations may be necessary in situations where the electrical system is serving a large number of appliances or where the appliances have unusual operating characteristics. In general, it's always a good idea to consult the NEC and other applicable codes and standards when designing or installing an electrical system. These codes and standards are designed to ensure the safety and reliability of electrical systems, and they provide valuable guidance on how to properly size and install electrical equipment. Now let's delve a bit deeper into the NEC and its relevance to electrical load calculations. The NIC, published by the National Fire Protection Association, or NFPA, is a widely adopted standard for the safe installation of electrical wiring and equipment in the United States. It's important to remember that the NEC is not a law itself, but it is often adopted by state and local jurisdictions, becoming a legal requirement. The NEC is updated every 3 years to reflect advancements in technology and address emerging safety concerns. It covers a wide range of electrical topics, from grounding and bonding to overcurrent protection and wiring methods. Article 220 of the NEC, titled Branch Circuit, Feeder, and Service Calculations, provides detailed requirements for calculating the electrical loads in buildings. This article includes information on how to calculate the general lighting load, the appliance load, the motor load, and other types of loads. It also provides guidance on how to apply demand factors to these loads. Demand factors are multipliers that are applied to the calculated loads to account for the fact that not all electrical equipment will be operating at its maximum capacity at the same time. These factors allow for a more realistic assessment of the electrical demand on the system. For example, the NEC provides demand factors for dwelling units, office buildings, and other types of occupancies. These factors take into account the typical usage patterns in these occupancies. When performing electrical load calculations, it is important to follow the requirements of the NEC. Failure to do so can result in an undersized electrical system, which can lead to overheating, equipment failure, and even fire. In addition to the NEC, there may be other applicable codes and standards that need to be considered. For example, some jurisdictions may have their own electrical codes that are based on the NEC but include additional requirements. It's also important to consider any applicable energy efficiency standards. These standards may require the use of energy-efficient appliances and lighting, which can reduce the overall electrical load in the system. Proper load calculation is crucial for several reasons. Firstly, it ensures safety. An accurately calculated load prevents overloading the electrical system, which could lead to overheating, insulation damage, and potentially fires. Secondly, it guarantees reliability. Correctly sized components such as circuit breakers and conductors, based on load calculations, minimize the risk of nuisance tripping and power outages. Thirdly, it promotes efficiency. Avoiding oversizing equipment through precise load calculations reduces initial costs and minimizes energy waste. Fourthly, it ensures code compliance. Adhering to NEC and local electrical codes is essential for legal compliance and safety certifications. To reiterate, let's revisit the example of calculating the demand load for a 16,000 watts range. You have a 16,000 watts electric range in a dwelling unit. The first step is to determine the demand factor for the range. According to NEC Table 220.55, the demand factor for single household cooking appliance rated over 1 and 3/4 kilowatts is 8 kilowatts. Since the range is rated at 16,000 watts, which is greater than 12 kilowatts, we need to increase the demand factor by 5% for each kilowatt or major fraction thereof that the range rating exceeds 12 kilowatts. The range rating exceeds 12 kilowatts by 4 kilowatts, so we need to increase the demand factor by 20%. 20% of 8 kilowatts is 1.6 kilowatts, so the adjusted demand factor is 9.6 kilowatts. Therefore, the demand load for the 16,000 watts range is 9,600 watts. This calculation demonstrates how to apply the NEC guidelines to determine the demand load for an electric range. While the alternate math method offers a shortcut, understanding the underlying principles and code requirements is essential for accurate and safe electrical system design. In addition to electric ranges, there are many other types of loads that need to be considered when performing electrical load calculations. These loads can be broadly classified into several categories, including lighting, appliances, motors, and heating, ventilation, and air conditioning, or HVAC equipment. Each of these categories has its own specific requirements and considerations. Lighting loads are typically calculated based on the square footage of the building and the type of lighting fixtures that are being used. The NEC provides tables that specify the minimum lighting load for different types of occupancies. Appliance loads are calculated based on the nameplate ratings of the appliances. The NEC provides demand factors for various types of appliances, such as refrigerators, washing machines, and dryers. Motor loads are calculated based on the horsepower rating of the motor. The NEC provides tables that specify the full load current for motors of different sizes and voltages. HVAC loads are calculated based on the heating and cooling capacity of the equipment. The NEC provides guidelines for calculating the heating and cooling load for different types of buildings. In addition to these general categories of loads, there may be other specialized loads that need to be considered, such as electric vehicle charging equipment, solar photovoltaic systems, and energy storage systems. These specialized loads may have their own unique requirements and considerations. When performing electrical load calculations, it is important to consider all of the applicable loads and to apply the appropriate demand factors. This will ensure that the electrical system is adequately sized to handle the expected load without being unnecessarily oversized. It is also important to consult the NEC and other applicable codes and standards to ensure that the electrical system is designed and installed in accordance with all applicable requirements. The principles discussed here regarding electric range load calculations extend to other appliances and equipment as well. Understanding the NEC guidelines and applying appropriate demand factors are crucial for ensuring the safety and reliability of electrical systems in residential and commercial buildings. Remember to always consult the latest edition of the NEC and local electrical codes for the most up-to-date requirements. Also, consider consulting with a qualified electrical engineer or electrician for complex load calculation scenarios. Understanding the different types of loads in a building is essential for accurate electrical load calculations. Let's delve deeper into each category. Firstly, lighting loads. Lighting loads are determined by the type of occupancy, square footage, and lighting fixtures used. The NEC specifies minimum lighting loads for various occupancies in volt-amps per square foot. For example, a dwelling unit requires a minimum of 3 volt-amps per square foot, while an office building requires 3.5 volt-amps per square foot. To calculate the total lighting load, multiply the square footage of the building by the volt-amps per square foot requirement. If using LED lighting, which consumes less power, you still need to use the minimum volt-amps per square foot specified by the NEC. Secondly, appliance loads. Appliance loads are calculated based on the nameplate ratings of the appliances. The nameplate rating indicates the maximum power the appliance can draw. For continuous loads, such as water heaters or refrigerators, the load is multiplied by 125% to account for sustained operation. For non-continuous loads, like dishwashers or washing machines, the nameplate rating can be used directly. The NEC also provides demand factors for certain appliances, which can reduce the calculated load. Thirdly, motor loads. Motor loads are determined by the horsepower, voltage, and phase of the motor. The NEC provides tables that list the full load current for motors of different sizes and voltages. This full load current is used to calculate the motor load. For single motors, the load is typically 125% of the full load current. For multiple motors, demand factors can be applied to reduce the calculated load. Fourthly, HVAC loads. HVAC loads include heating, ventilation, and air conditioning systems. These loads are typically calculated based on the heating and cooling capacity of the equipment. The NEC provides guidelines for calculating the heating and cooling load for different types of buildings. The load can also be determined from the nameplate rating of the equipment. For HVAC equipment, the load is often considered a continuous load and multiplied by 125%. Understanding the characteristics of different loads and applying the correct demand factors are crucial for accurate electrical load calculations. This knowledge ensures that the electrical system is properly sized to handle the expected load, preventing overloads and ensuring safety and reliability. Let's explore some additional considerations for specific types of equipment. Firstly, electric vehicle charging equipment. Electric vehicle, or EV, charging equipment is becoming increasingly common in residential and commercial buildings. The NEC provides specific requirements for calculating the load for EV chargers. The load is determined by the output current of the charger and whether it is a continuous or non-continuous load. For continuous loads, the load is multiplied by 125%. Secondly, solar photovoltaic systems. Solar photovoltaic, or PV, systems generate electricity from sunlight. The NEC provides guidelines for calculating the load for PV systems. The load is determined by the inverter output current and the system voltage. The load is also affected by the location of the PV system and the available sunlight. Thirdly, energy storage systems. Energy storage systems, such as batteries, store electricity for later use. The NEC provides requirements for calculating the load for energy storage systems. The load is determined by the output current of the system and the system voltage. The load is also affected by the type of battery and the charging and discharging characteristics. When dealing with specialized equipment like EV chargers, PV systems, and energy storage systems, it is essential to consult the NEC and other applicable codes and standards. These codes and standards provide detailed guidance on how to properly size and install the equipment. They also ensure that the equipment is safe and reliable. In addition to calculating the load for individual pieces of equipment, it is also important to consider the overall load in the electrical system. This includes the sum of all the individual loads, taking into account any applicable demand factors. The overall load is used to determine the size of the service entrance, the size of the feeder conductors, and the size of the overcurrent protection devices. If the overall load is not calculated correctly, it can lead to an undersized electrical system. This can cause problems such as voltage drop, overheating, and equipment failure. It can also create a fire hazard. Therefore, it is crucial to perform accurate electrical load calculations to ensure the safety and reliability of the electrical system. It is always recommended to consult with a qualified electrical engineer or electrician for complex load calculation scenarios. Their expertise can ensure that the electrical system is designed and installed in accordance with all applicable codes and standards, providing a safe and reliable electrical system. Keep in mind that this overview is a general guide, and the specific requirements for electrical load calculations can vary depending on the location and the type of building. Always consult the latest edition of the NEC and local electrical codes for the most up-to-date requirements. Also, consider consulting with a qualified electrical engineer or electrician for complex load calculation scenarios. Finally, proper electrical load calculations are not just a matter of code compliance, they are also essential for ensuring the safety and reliability of electrical systems. By taking the time to perform accurate calculations, you can help prevent electrical hazards and ensure that your electrical system is operating safely and efficiently.